Welcome to Deep Silicon VLSI YouTube channel. Let's have another design challenge. The question, draw output waveform for this given design. It has NOR gate, NOT gate and NAND gate. So guys, first of all, if you want to find out the waveform for this X, you need to know what is a Boolean function by this design. Let's find out that. B bar. Therefore, this is A plus B bar whole bar. Now what you get? It is like, let's keep it as it is. We will do at the end. Now this is X, output. X is A plus B bar whole bar into B whole bar. Got it? Now, by using De Morgan's theorem, A plus B bar whole bar plus B bar. This can be written as A plus B bar plus B bar. It is A plus B bar only. So guys, here the given design is giving you the Boolean function A plus B bar, so that the output follows A plus B bar. They have given A, B inputs. These are the waveforms. Of course, this off period is 10 milliseconds and this is on period is 10 milliseconds and this is 5 milliseconds, 5 milliseconds. Got it guys? For better understanding, we are entering into graphical representations. Location change. Here the inputs are A, B, whose input A time period is 20 millisecond. So 10 millisecond, 10 millisecond. Whereas B 10 milliseconds. So it's a 5 milliseconds, 5 milliseconds. Okay. Now as per the design, we got the output X as A plus B bar. Anyway, A input is available. We want to know regarding B bar. B bar is simply the inverse of B. Hence, here we get logic 1 in place of logic 0. Similarly, logic 0 in place of logic 1. Hence, this one guys, this is about B bar. So we want to draw now the output X, graphical representation. Now here the input is B bar and A. So in this case it is 1, 1. Hence output will be 1 only. Again 1, 0, 1 plus 0, 1 only. Similarly 0, 1, 1 only. Again here 0, 0, then output becomes 0. This one. Now the same guys, same will be repeated, no? 1, 0, like 1, 1, 1, 0, 0, 1, 0, 0 means 1, 0, 1, 0. Hence, you get 1, 1, 1 and 0. This one. Likewise. Okay guys. So, here the output waveform on period is 15 millisecond and off period is 5 millisecond, because we assumed this as 20 milliseconds. Each box is 5 milliseconds, let's assume. Therefore 15 millisecond and 5 millisecond. With this we can tell the output waveform for the particular design is this. Welcome back. Now you understood how we got the output waveform like this. Yes, no issue. But guys, there is one shortcut, trick you can say, which is very easy to solve this question even without graph paper. Yes, do you want to know? Let's dive into that solution. Guys, that is, see here the A. What is the sequence, guys? The bit pattern? It is like 1, 1, 0, 0. Again 1, 1, 0, 0. The waveform is a periodic, it's getting like repeated, isn't it? Yes. Similarly, B, if you see, B is like 0, 1, 0, 1, 0, 1, 0, 1. So, B is 0, 1, 0, 1, 0, 1, 0, 1. But what is the output expression for this design? A plus B bar. You want B bar, right? Means replace 0 with 1, 1 with 0. Therefore, B bar will be 1, 0, 1, 0, 1, 0, 1, 0. Done. Finally, we want to know the output X, which is A plus B bar means this and this, isn't it? Yes. Now, you add 1, 1 plus 1, 1, 1 plus 0, 1, 0 plus 1, 1, 0 plus 0, 0. In the same way, like this. So, 111, 1 means 5 volts. So, for 3 bits, the logic high. That means this 5 milliseconds, right? 5 milli, 5 milli, 5 milli. 15 milliseconds. And for 1 bit, it is logic 0. So, 5 milli. In this way also, we can determine the output waveform. So, you can draw the waveform simply in this way also. Right? Let's have another design challenge. Let A is equals to C is equals to 0 and B is equals to 1 until time t is equals to 0. At t is equals to 0, all the 3 inputs flip. That means 0 becomes 1, 1 becomes 0. And remain in that state. For t greater than 0, output Z is equals to 1 for a duration in nanoseconds of. Actually guys, remember, in these kind of design challenges, wherever near the logic gates, if they give any some like time period, it is a propagation delay. So all the logic gates have identical propagation delay, that is 20 nanoseconds. Let's take the old case, the previous case 1 you can say, that is A is equals to 0, C is equals to 0 and B is equals to 1. Therefore guys, this becomes 0. This becomes 0 and again 0, 0. You will get Z is equals to 0. This is until time t is equals to 0. Now at t is equals to 0, they have changed the inputs. They flipped. Therefore, this becomes 1, 0, 1. Therefore, here you get 1. This becomes 1 into 1, 1. Then Z is equals to 0 only, na? Because XOR gate, different inputs are not there. We all think output will be 0. Yes, of course. Even though the inputs got flipped, output will be 0. But when it is possible? When the logic gates are ideal. That means propagation delay is 0. In such case, output will be 0 only. But in this given design, the logic gates are non-ideal. They have some propagation delay. So for that better understanding, we are entering into graphical representation. Here, the output of AND gate, let's assume it as Y. And this will be like B bar. Suppose if you want to draw the waveform for Z, you need to know about Y. Anyway, C is given. So you need to know about Y. Similarly, B bar as well. Now, coming to the direct point, we want to draw B bar, which is simply the complement of B, which is this. However, guys, all the logic gates have non-zero propagation delay, that is 20 nanoseconds. So that here if you want to draw the waveform for B bar, where the input is changing from 1 to 0, it will take 20 nanoseconds. So that let's draw here after 20 nanoseconds this. Okay guys, so here I am assuming one box is 10 nanoseconds and this will be 20 nanoseconds, right? Similarly, now I want to draw for y as well, this one, which is simply the logical multiplication of a and b bar. Now guys, here anyway it's 1 into 0 0 only, and here especially you can take this, it's 1 1, then output will be logic 1, but after 20 nanoseconds, therefore here it will be like this, from here after 20 nanoseconds, this one guys. So whatever the change is appeared here is going to replicate on the output y after 20, then what will be the value here? Definitely 40 nanoseconds. Got it guys? Fine. Even the same you can replicate at B also. Here B has changed, but that appeared on the B bar after 20 nanoseconds. Now it's time to draw about output Z. Here XOR gate is there. The inputs are YC. So now the inputs are Y and C. Let's change the color for a better graphical representation. Now guys, here you can say it's 0 1 0 1 1 1. Similarly it's a 1 1 kind of things. Yes, now the first change, the C has changed from like 0 to 1, right, and that will appear at the output after 20 nanoseconds. Hence here the output will be like this 0 to 1, because of that output will be logic 1 because of XOR gate. That happens after 20 nanoseconds, and yes, again it is 0 1, it's carry forward, but here again the output y has changed from 0 to 1. Because of this change, again output will be changes, because it's 1 1 0 we will get, but 0 you get after 20 nanoseconds. Hence here exactly from here 20. So after 20 output will changes from 1 to 0. This change will appear on this output after 20 nanoseconds. This is output Z. So here I can say that here the output is 1 for nearly 40 seconds, because the duration is like this 1 2 3 4, 40 nanoseconds time period, the output is logic 1. This is because of purely non-zero propagation delay. Hope you understand. The propagation delay plays a very important role in digital designs. Okay. So guys, the output waveform for a non-zero propagation delay is this. Hence, the output Z is equals to 1 for a duration of this one, that's none other than 40 nanoseconds. And guys, these sharp transitions, for some 40 nanoseconds the output becomes 1 and again it's 0. We are expecting 0, but because of non-zero propagation delays, these you are getting, and these are called glitches. Okay guys, so glitches are very harmful in VLSI designs. When you are making designing a chip, glitches plays an important role and you need to be very careful regarding them. Let's have another design challenge. For a given design, we want to draw the output waveform. Remember guys, in all the VLSI placement examinations or even interviews, don't expect any questions like in terms of multiple choice or fill in the blanks. No, they'll give you the question, you need to explain, means they are expecting the descriptive answers. Okay, now let's enter into the question. The design has two logic gates. It's a NOT gate only because the inputs are tied together. This is a XOR gate. The propagation delay of a NOT gate is 10 nanoseconds, XOR gate 20 nanoseconds. We want to draw the output waveform, this one. How to draw? The given input is, at t is equals to t naught, the input is changed from, switched from, flipped from 0 to 1. In such case, what will be the output? After t is 0, you can consider. What is a waveform? You need to know. Okay? So for better understanding, we are entering into graphical representation. Let's have graphical representation for the given problem. The design has a NOT gate whose propagation delay 10 nanoseconds, XOR gate 20 nanoseconds. The given input Vi is this. At t0 time period, the input has changed from 0 to 1. Now we want to draw the waveform for V0. If you want to draw the waveform for V0, you should know the output of NOT gate, okay, which is Vi dash, Vi bar. Even though it is a NOR gate guys, as the inputs are tied together, it can be treated as a NOT gate only. Now here, first let's consider Vi dash. It has propagation delay 10 nanoseconds, hence the output changes from 1 to 0 after 10 nanoseconds from the T naught. So here let's consider this. Okay guys, whatever the T naught has changed from 0 to 1 is going to impact on the output of G1 after 10 nanoseconds. Okay guys, let's consider this as T1 and this is anyway T0. Now here you see we want to draw the waveform for V0. Let's draw V0. Coming to that, here Vi dash and Vi, isn't it? So this and this. First change here as it is previously before T0. You can say here this is before T0. As the inputs are 0, 1, output will be logic 1 itself before T0. Yes, at T0 input has Vi is changed from 0 to 1. Therefore, it is 1, 1. Hence, output becomes 0. That will happen after 20 nanoseconds. XOR gate. So, from here, after 20 means, let's assume each box has 10 nanoseconds. Therefore, here output changes from 1 to 0. Okay, guys. So, whatever the T0 input has changed, that appeared at the output after 20 nanoseconds. Similarly, let's take about T1. Again at T1, it's a 1, 0. Means output will be logic 1, but that will happen at the output after 20 nanoseconds. Whatever the T1 has changed from 1 to 0 appear at the output after 20. So, from here whatever the 20 means, 2 boxes means here, it will change from here, this one. So, that output will be here in between 0. Hence guys, here this is T2, T3, T4 and etc. T5. Okay guys, so here what I mean is till T2 the output is logic high. Between T2 to T3 output is logic 0, because whatever the T1 change in the T1 will appear at the output after 20 nanoseconds. This is the period, right guys? So this is the one guys. Welcome back. So guys, for this given design with the non-zero propagation delays, the output waveform is this. Here usually if there is no propagation delay, if you see this XOR gate, it's a NOT gate. You are giving Vi, whatever might be the Vi. But here because of this NOT gate to this XOR gate, we will get complement of inputs. If this, let's assume this is Vi, here you get Vi bar, here you get Vi. Hence XOR gate output is always logic 1 only because of different inputs. But because of the propagation delay, you are getting some sharp transition. See, here also the output is high only, but for some time it is logic 0 also. This is the biggest problem called glitches in combinational circuits because of the propagation delay. Okay guys, and here hope you know we assumed here T1 is T0 plus 10 nanoseconds. Similarly, T2 is T1 plus 10 nanoseconds, like that. This is the importance of glitches in combinational circuits because of the propagation delay, right? Let's have another design challenge in terms of propagation delay. Yes. For a given input A, how many transitions occurs at B during the interval from 0 to 10 nanoseconds? This is the given input. Means at 1 nanosecond the input is shifted from 0 to 1, logic 0 to logic 1. In such case, what will be the output, I mean the waveform or the number of transitions in the output waveform? At B, the design contains 2 XOR gates and 2 buffers, and here the twist is the XOR gates propagation delay is 0 and the buffer's propagation delay is 2 nanoseconds, 4 nanoseconds. And you can ask me, sir, how it is possible in a practical way? A logic gate may have like a non-zero propagation delay, isn't it? Yes, obviously. But here the XOR gate doesn't have any propagation delay. Yes, it's a design challenge. Don't question the question. You need to take the question as it is. This is the design challenge. For that, you need to draw the waveform. That's it. These kind of situations only arises in VLSI, right, like written tests. Okay guys, now without any delay, let's start the solution. For the better understanding, we are moving to graphical representations. The given design is this. It contains buffers which has a propagation delay 2 nanoseconds, 4 nanoseconds, and there are 2 XOR gates as well. These are ideal. Okay guys, that means the propagation delay is 0. Okay, now come to the point. We want to know the output waveform B so that you can find out the number of transitions, etc. How to draw the output waveform B? If you want to know, here this buffer output you must know, so that you can tell the output waveform of B. Let's assume this is C, D and this is E. If you know DE waveforms, then you can draw the waveform of B. Similarly, if you know C waveform and A, you can draw the D. Okay, now let's enter into the question. Guys, here this is A, input it's A. We want to know the C. What is C? It's a non-inverting buffer only. It's simply buffer, means output is same as input. However, there is a propagation delay 2 nanoseconds, means here at 1, right, After 2 nanoseconds means 1 plus 2, 3. So the same you get like this. Okay guys? After 2 nanoseconds. Similarly, you can see here the D output. Coming to the D output is an XOR gate. Simply you need to choose inputs and then output, no propagation delay at all. Therefore, it is 1, 0. Then guys, definitely you will get output as logic 1. Isn't it? Yes. Is there any propagation delay? No. It's ideal. And then again here like this. Then it is 0 because it's a 1, 1. As these are ideal XOR gates, you don't get any propagation delay shifting at all. Now, we want to draw the waveform of E. What is E guys? Simply the waveform only, but propagation delay 4 nanoseconds included. So now here whatever the 1 plus 4, 5. So at 5 the output will be logic 1. The same as it is, but after 4 nanoseconds. This one guys, this is DE. Now we want to draw the waveform for B, the actual output. Now guys, this D and E are given to the XOR gate, ideal. Therefore, wherever the output is, inputs are different, D and E inputs. Then we will get the output as logic 1. See here, you can understand clearly. Here and here. In these two cases, the inputs D and E inputs are different. Hence, in that region, we get output as logic 1. In remaining places, it is 0 only. Okay guys? Yes. This is the output waveform of given design B. Welcome back. Now guys, the output waveform, this one. Like, did they ask you to draw the output waveform? No. They're asking you how many times the output waveform gets transition. To say 0 to 1 or 1 to 0. That's what here. How many transitions occur at B during the interval from 0 to 10 nanoseconds. See, from here 0 to 10 nanoseconds till here. How many transitions occur? You see the output waveform. Here there is one transition. Means like it is from 0 to 1. Transition number 1. Similarly, this is transition number 2. From 1 to 0. Similarly, transition number 3. Here from 1 to 0, transition number 4. So I can say that now, as per the given input, the given design, output waveform has the 4 transitions in between 0 to 10 nanoseconds. So the answer is here 4 times. Right guys? See, this much plays a key role. That's a propagation delay. Here actually whatever might be the input, here the XOR gate, like we get as it is, like here you see like this A and this is A only, buffer no. So you get A. For same inputs what you get? Output as 0 only. Now the same you are going to again to this. Means what I am saying is for this XOR gate, both the inputs are same. Then output must be 0 only. But because of the non-zero propagation delay of logic gates, you are getting some transitions called glitches at their output. The output is 0. But for 2 nanoseconds, the output is logic 1. You need to be very careful during the design with respect to the glitches, unwanted transitions. You can say glitches as unwanted transitions. Okay guys, let's have another design challenge in terms of propagation delay. Guys, here, this is the given design. There is a NAND gate and two NOT gates, and they are also called as inverters. The twist in this design is they said there is a propagation delay, but they haven't mentioned. They said some non-zero propagation delay. Now what about the output? And still they are not asking you draw the output waveform. How the output waveform looks like? Is it stays high output only, low output only, low to high, high to low, or high to low, low to high? So this is what the given design challenge, and we want to crack it. Yes. Okay. For a better understanding, we are moving to graphical representation. The given design is this. It contains 3 NOT gates and 1 NAND gate. The biggest challenge in this question is they said there is a propagation delay, but they haven't given, and all are identical. So whether it is a NOT gate or NAND gate, it has a equal propagation delay. Okay, for better understanding, we are assuming the propagation delay as 10 nanoseconds. The test signal, they said previously it was 0, logic low, and it has shifted to high. This is the test signal. And if you want to draw the output waveform to solve the given question, you need to know the point here. Let's consider this as test bar. If you know test bar signal, then test and test bar signal you can apply. You can perform NAND operation and you can get the output. So here, as there are 3 NOT gates, you can get it as a NOT gate only, because this A bar, whole bar, whole bar, it is A bar only, right? So here, as there are 3 NOT gates, this path will introduce 30 nanoseconds delay. Hence, the test signal has shifted from logic 0 to logic 1. However, the test bar signal will appear change in the output from 1 to 0, because it is a 0 to 1. Now it is 1 to 0, but after 30 nanoseconds. Therefore, from here, after 30 nanoseconds, here we are assuming each box 10 nanoseconds delay. Hence, whatever the change occurred here, that appeared at the output test bar after 30 nanoseconds. Got it? Fine. Now it's time to discuss about the output waveform. Simply it is NAND operation of test and test bar. Here first of all, previously it is 0 into 1, 0 whole bar 1. You will get output as logic 1 till here, right? Now as the test signal shifted from logic 0 to logic 1, there will be change in the output, because 1 1, it is logic 0. Hence here it happens after 10 nanoseconds only. Because of this NAND gate, there is a delay. We are assuming it as a 10 nanoseconds, and you can take it as 20 or some other value. So here after 10 nanoseconds, output is shifted from logic 1 to logic 0. Okay, fine. So here what I am telling is, because of change in the test signal, output is changed like this. Fine. Now again test bar signal also, because it is 1 only, test bar has changed at this point. Let's assume this is 0, this will be 10, 20, 30. Okay, wherever like at 30 nanoseconds the test bar signal has shifted from logic 1 to logic 0, then 1 into 0, 0, 0 bar 1, we will get output as logic 1, but will you get immediately? No, it has a propagation delay 10 nanoseconds, means from here 10 nanoseconds, after 10, from here it is shifted from logic 0 to logic 1. Hence guys, here the output waveform looks like this, that is, here you can say 0, 10, 20, 30, 40 nanoseconds, etc. This is what the output waveform. Okay. Welcome back. Now guys, from the previous discussion, using graphs, we understood the output waveform is like this. Here, if you see that how the output waveform has changed, it is shifted from logic 1 to logic 0, high to low, and then low to high. Hence, the right answer is option D. It pulses from high to low and low to high. That's it. Guys, here, this is the importance of glitches, or the whatever the consequences due to propagation delay. Yes, so they said some non-zero propagation delay. This is a NAND gate. For NAND gate, if you take the output like 0 0 0 1 1 0 1 1. Now if you see that the truth table y is equals to AB whole bar, we will get 1110. That means whenever the one of the input is logic 0, output is logic 1. And when both inputs are logic 1, output is logic 0. And especially you take these two cases, 0 1 1 0, output is 1 only. That means to a NAND gate, let's assume two inputs. In such case, when inputs are different, output is logic 1 for a NAND gate. Hence, here you take this design, here test signal, and here what you get? Test bar. Because this is A bar, whole bar, whole bar. Then it is A bar only, test bar only. There are two different inputs, test bar. Hence, either you get this or this. In such case, output is logic 1, but still, for some time, output is 0 only. From 10 nanoseconds to 40 nanoseconds, let's assume. By assuming each logic gate has a 10 nanoseconds propagation delay. So, this is what here the consequences due to the propagation delay. Okay guys, so this is a complete marathon for this particular propagation delays. Right guys, thanks for watching and see you in the next video. This is Shivram signing off. Jai Hind.